One, go.
Good morning to all respected faculty and peers. Today I'll be presenting our project on paddy crop disease detection using ANN, CNN and RESNET 101. This project was done by myself, Annie Gibian Srinivasulu, along with my teammate Harish Raguru. The main aim of our project is to apply deep learning techniques for the automated detection of paddy leaf diseases. Rice is one of the most essential crop in worldwide, but it is vulnerable to multiple diseases that affect crop yields. The project explores how artificial intelligence can be utilized to provide timely solutions to these challenges. By comparing ANN, CNN, and ResNet 101, we aim to identify the most effective method for our accurate detection of leaf diseases. uh, The finding of our work can help farmers in early detection and reducing their losses and improving food security. The title of our project captures the essence of using modern AI approaches for agriculture, and excited to walk you through our methodologies, experiments, and results with this introduction. Let us begin the introduction slide. Paddy is one of the most widely grown staple crop, and it is vital to the food security of billions of people, especially in Asia. Unfortunately, its production is highly affected by diseases such as leaf blast, brown spots, and Hispa, which can cause severe yield losses. Traditionally, detecting these diseases require expert knowledge or manual inspections by farmers, which are not always reliable. These manual methods are time consuming, error prone, and impractical for large scale farming. This problem highlights the need for automated intelligent solutions that can detect diseases efficiently and accurately. In this context, machine learning and deep learning have emerged as powerful tools for image recognition tasks. By analyzing leaf images, these methods can classify different diseases with high accuracy. Our project especially focuses on comparing three deep learning models to evaluate their effectiveness. The goal is not only to test their accuracy but also to demonstrate how technology can assist agriculture with increasing food demand. Adopting such solutions is more critical than ever. This introduction sets the foundation for the motivation and direction of our project. Harish, next slide, please. The dataset we used for this project is the Paddy Doctor dataset, which we obtained from Kaggle. This dataset is highly suitable for our task as it especially focuses on paddy leaf disease detection. It consists of 6,061 images of paddy leaves divided into four classes: healthy, leaf blast, brown spot, and Hispa. Each class is well represented with a sufficient number of images, making the dataset balanced. Balanced datasets are crucial because they prevent models from becoming biased towards certain classes. In our dataset, no single class dominated the others, which ensures fair modeling training. The images are of varying qualities and conditions, closely resembling real world farming scenarios. The diversity in the dataset allowed the models to learn generalized features. Kaggle, being a reliable source, further added credibility to the dataset quality. Overall, this dataset was ideal for testing and performing of ANN, CNN, and Reset 101, ResNet 101 on paddy diseases detection. It ensures that our evaluation was realistic and meaningful. Thus, the dataset formed the foundation of our experimental setup. Before training these models, we performed several pre-processing steps to prepare the dataset. Pre-processing ensures that the data is cleaned, consistent, and suitable for machine learning tasks. First, we normalized all images to the pixel values fell within a standard range, which speeds up training and improves performance. Normalization also make sure that different lighting conditions or intensity variations do not affect the model's learning. Next, we shuffle the dataset to eliminate any hidden ordering or bias that might affect training. We also split the dataset into training and testing sets in an 80:20 ratio. This splits allowed the model to learn on a majority of the images and then be evaluated on unseen data. The test set severe, I mean, this test set served as an unbiased benchmark for the model performance. Pre-processing steps, though simple, play a huge role in accuracy and reliability of the results. Without proper pre-processing, even the best models may fail to perform effectively. Therefore, we carefully design the steps to create a solid pipeline for model training. This ensures consistency across all three models. From next slide, my friend Raguru Harish will continue. Thank you.
Thank you, Annie. So now first look at the first model that we have implemented, which is artificial neural network. So here ANN is one of the simplest deep learning models, which consist of multiple fully connected layers. These layers process the input data by flattening the images into vectors, which limits the model's ability to learn the spatial features. Like ANN was also able to detect some basic patterns, but struggle with the complex image data. So as a result, the accuracy that we have achieved in this was only around 65%. Even when you check the confusion matrix, it showed a significant misclassification among the disease categories. So this includes that the AN could not effectively like differentiate between the similar looking diseases. Like while ANN served as a good starting point, but its limited performance highlighted the need of more advanced models. Despite its weakness, AN provided us with a baseline to compare other models against. So in real world applications, such performance would not be sufficient for this reliable disease detection. Therefore, like AN set the stage for us to explore more specialized architectures like CNN. So it was useful for showing the limitations for the simple neural networks in this domain. Even when we check here in the confusion matrix across the diagonal, we don't see good numbers. The numbers are all splitted. So this itself proves that it has its performance not being that good. So coming to the CNN, which is convolution neural network. After ANN, like we applied the CNN, which is widely used for image classification tasks. So CNN uses the convolutional layers that can scan the image with filters to detect the features such as edges, textures, and also the shapes. The pooling layers feature reduce the dimensions of the data with preserving most important features. So this structure makes the CNN particularly strong in handling image data compared to the fully connected networks. So in our experiment, CNN achieved an accuracy of around 94%, which was a significant improvement over when compared with the ANN. Even the confusion matrix showed few misclassification, like very few. As you can see along the diagonal, the numbers are good, but there's a small distribution of misclassified numbers. Apart from the diagonal. So the CNN strength actually lies in its ability to automatically extract the spatial hierarchies from the input images. So this allows it to perform better in recognizing like visual patterns compared to the ANN. However, it still showed some errors in distinguishing closely resembling disease categories. Despite this, CNN demonstrated why it has become the standard for many computer vision tasks. Its performance validated the importance of convolutional architectures for agriculture disease detection. So coming to the RESNET 101, finally we implemented this RESNET 101, which is one of the most advanced architectures used in the image recognition. So in this ResNet 101, it is a deep residual network that has like 101 layers, which allows it to capture very complex and also the abstract features from the images. So this unique feature of ResNet is its skip connections, which solves the vanishing gradient problem that occurs in very deep networks. This also allows the network to learn effectively without losing the information across layers. So we use this ResNet 101 with the transfer learning, where the models pre-trained on a large data set and it has been fine-tuned on our Paddy dataset. So this approach provided the model with like prior strong knowledge and also improving its learning efficiency. In our results, we also achieved impressive accuracy of around 98%. Even the confusion matrix also showed like a minimal misclassification across the diagonal. We can see the numbers are very good, and there's a small distribution of the misclassifications, which indicates its superior ability to differentiate between the disease classes. So compared to ANN and also CNN, ResNet clearly outperformed them by a wide margin. So this results proves the power of residual networks in tackling the real world classification problems. So ResNet not only gave the highest accuracy, but also demonstrated the stability across the different classes actually. Over to you, Annie.
Compared the results of all three models, the difference in performance was clear. ANN achieved only 67% accuracy, making it weak and unreliable for this task, where CNN improved accuracy to 93%, showing its strength in image feature extraction. ResNet 101 performs, it performed best with 98%, proving its superiority in handling complex image recognition. This progressive improvement demonstrate how model complexity affects accuracy. ANN lacked the power to detect spatial hierarchies, and CNN improved by capturing local features, and ResNet excelled with deep layered learning. The confusion matrix for each model further emphasized these differences. ANN misclassified multiple classes, and where CNN reduced errors, and ResNet minimized this uh, almost entirely. This results clearly shows that deeper and more advanced architecture delivers better outcomes. Our discussion highlights how machine learning can revolutionize disease detection in agriculture. With ResNet 101's performance, we can confidently recommend it for practical use. Thus, the results strongly support the adoption of advanced AI in crop monitoring. Next slide, please. To conclude, our project demonstrated the application of deep learning for paddy disease detection. Among the three models tested, ResNet 101 clearly outperformed ANN and CNN, achieving an accuracy of 98%. This improves that advanced architectures with the transfer learning are highly effective for agriculture applications. The project highlights how artificial intelligence can play a major role in helping farmers detect diseases early. By doing so, it can reduce crop losses and improve yield. However, there are still areas for improvement and extension. For example, future work can focus us on building real-time mobile application for farmers to use in the field. And additionally, larger and more diverse data sets can be collected to further strengthen and models robustness, integrating whether the data and soil condition could also make predictions more accurate. Thus, this project serves as both a proof of concept and foundation for future research. It clearly shows the promising potential of AI in modern agriculture. Next slide. This concludes our presentation on paddy crop disease detection using ANN, CNN, and RESNET 101. In this
And
project, we
thank you,
saw,
everyone. Uh, so here ends our presentation. And next, we'll be going through our setup, like how we shared, how we performed, and everything. Hello, everyone. So now we'll be walking you through the working model of our project. So let me share the screen and show you how we do it. And is my screen visible?
yes,
Okay, so we have as the coding part has been done in by using Python, and we have used the OpenCV2 library for the resize the data set and get all the data set to equal pixels and similar size. And also we have used the TensorFlow for the model building and all the libraries Pandas, NumPy, and everything. So once also we have developed a small interface where we perform each and every single task in just one click so that we need not run by selecting the whole program individually and going through that. So when once we run the program, it takes a while for running and a small interface opens which we developed where we can easily generate the results. So here is it. So first, as a first step, we'll be uploading the disease dataset which we have collected from the Kaggle. So we select the dataset which we would like to perform the analysis, and once we select it, it automatically takes the dataset, processes, and everything. And a small result has also been added by us so that we can see like the model is has the loaded the data set or not. So out of the whole data set, it has been categorized into four things. And here you can see how many leaf blast images and how many brown spot and how many Hispa and healthy images are there in the whole data set. So this we have added because we can check whether the data has been processed successfully or not. After that, then we pre-process the data set, which is by splitting them into 80-20%, 80% for the training data set and 20% for the test data set. So on whole, we have 6,061 images in which the 80% randomly took 4,848 images, and the rest 20%, which is 1,213, has been splitted randomly in between them. So so once the data set has been pre-trained, now we'll go with the ANN algorithm and see how the model performs. So once we click the ANN algorithm, it generates a confusion matrix, and also we can see the results on the left hand side. It The ANN algorithm did not perform that good. As you can see, it has not spotted the brown spot ones. It has many brown spot images has not been detected as a leaf blast or Hispa because of the model performance and its low clarity on the pixels. Here you can also see that the accuracy is all we have achieved is only 66 percent, and even the F1 score is also very less. So because of this, we have moved to upgraded to a better algorithm, which is a CNN. So when we run the CNN algorithm, after running the CNN algorithm, here you can see the results. It's definitely very, very better than the ANN. And you can see the results on the left hand side in numbers, which is accuracy we got around 95. And also the F1 score all has been improved. Even in the confusion matrix, you can see a very small distribution. Apart from the diagonal, you can see so diagonal stays strong here. Still, we wanted a better results. That's why we have moved on to the RESNET, which gave us the better results than both. So when we run the RESNET algorithm, it has calculated everything, and we got the confusion matrix and results and everything. Here you can see. After running the algorithm, we can see on the left hand side as well the accuracy almost has been improved by 2%, which is better than the CNN. And also the everything like F1 score and recall, even which can be seen in the confusion matrix. The diagonal is very, very, very strong. Only very few has not been detected by this algorithm, and which can be seen here. Almost like we missed only like a 2.5% accuracy, where we see the distribution, which can be seen here. Now, when we so this stands out among the three, and this can be recommended for the thing. And we also developed a small comparison graph among these three, just to show you how which model performed what percentage of thing. And as mentioned, the ReasonNet is a standalone among the three. So after executing, we came to know that ReasonNet will be the best suitable one, and also we randomly took a small test data set, and we tested whether the model is performing well or not, like detecting the diseases or not. So we have added a one more thing, like where we predict the from the test image the diseases. Let's just randomly select anything like seventh one image. So now here you can see, as you can see, there are few spots on the paddy crop disease. So here you can see the paddy is detected as a brown spot, which has been detected correctly. Or else we can test one more different one. Let's go the randomly. Yeah, six. Okay, maybe. So here you can see there is no any spots or any crops on the side, and this looks healthy, which the algorithm also has predicted as healthy. So this looks good. And let's just randomly select maybe 11. And here you can see there are some bad crops next to the paddy crop, which the thing has detected exactly, which is Hispa. Also, we can select one more, maybe scroll, yeah, maybe two. Here you see the leaf blast. Here, as you can see here, the crop has not been. Here in this spot, it has been diseased, which is the leaf blast disease. And here you can see it has detected correctly. One more run, we can close on maybe like five. Here you see there is no spots or any blasts or no extra crops on the side, so it has been detected as healthy. So with this model, like you said, it will be helpful for the farmers to detect the disease early on. Like we say, prevention is better than cure. So we have developed this model, and hopefully it will be useful for the farmers in detecting the disease early on. And there are few, like we discussed previously, few future scope work which can be attempted by anyone in reference to this project. Thank you, everyone.